All right, so hopefully this will work. Sedimentary rocks. Can y'all see the PowerPoint?
Yeah.
Okay. Yay, I'm doing this right, woohoo. Yay. Okay. Cool, thank you. All right. So sedimentary rocks make up a large part of the crust of the earth. Most of the land crust or continents and pretty much all of the ocean basin crust. But it's very, very thin. The crust is very thin, so sedimentary rocks cover only about 10 miles deep into the crust. That's very thin compared to the whole size of the planet. One big thing about sedimentary rocks is there's so many different clues about what an environment was like in the past in a particular spot. So if you were standing at the road cut on exit 125, very carefully, if you're looking at that cliff or that piece of rock, that it's called an outcrop, if you can actually stand there and look at a section of rock. If you're standing at that outcrop, then it's all limestone, but it's a little bit different in different spots as you go older. So the youngest rock will be at the top, and then as you go down towards the road, from the top down, the rocks get older. So if you look at one particular spot, you can see the differences that occurred over time. This is part of that working backwards that I told you about. Usually geologists will talk about what's at the surface first and then go back in time. That's really cool. That's part of paleontology. Yeah, that's actually a neat part of paleontology. So also sedimentary rocks contain all the coal we know about, oil, natural gas, also the ores that we mine for uranium, iron, aluminum, and probably most importantly is groundwater, which we'll talk about later. But in Kentucky, groundwater is where we get most of our drinking water through that resource. So sedimentary rocks, basically, you start with a rock, doesn't matter what kind it is, it gets beaten up, broken down, weathered, whether physically or chemically by sunlight, water, rain, cold, freezing, and thawing. And then sediments are transported downhill, right? Everything goes, gravity pulls it downhill, either just by its weight or by water transporting it somewhere else. Then they're deposited in another place. So sediments get buried continuously, time after time and over time. And I just thought, so you could probably see this, when they dug up Greek ruins, they dig down, or Egyptian old cities, they dig down and, okay, we're at about this year, and they dig down further to see how much older they can find artifacts. Well, it's the same thing. Sediment is just covering and covering and covering over time. As the sediments are buried, they are put under more and more pressure. And also, with all that pressure comes heat from compaction from the pressure. So that turns the sediments into rocks, and that's called lithification. So lithified turns the sediments into rocks. We're going to look at 3 different classes or types of sedimentary rocks. We got detrital, chemical, and organic. Chemical and organic kind of in some places, some books lumped together, but there is a little bit of a difference. Typical origin of sediments. Glaciers move sediments pretty well, fairly transport them pretty far. Usually water's the more common way of transporting sediment. If you're looking at the Mississippi River, it's really brown. That's sediments being transported by the water. Okay, so detrital sedimentary rocks, basically they are made up of particles. You can see the particles, or maybe you can't. Maybe they're too small to see. But if you look at them under a microscope, you can see the particles of the minerals or previous rocks that they're made of. Mostly they're going to contain quartz, the feldspars, one of those or both of those two micas you saw last night, and clay minerals. So what you're going to do to identify detrital sedimentary rocks is looking at the particle size. Can you see it? If you can't, then you kind of have to use some other ways to figure out what you got. Particle size will also help you figure out what the environment was like when and where those sediments were deposited. And most common ones are shale, sandstone, conglomerate, and breccia. All right. So at the top there, we've got conglomerate and breccia, mostly greater than 2 millimeters. That's the largest particle. Those pebbles are in a very finer grained material, and it's probably like a clay, but you're looking at the largest particles you can see. So you can tell a conglomerate has rounded particles, and a breccia has more angular particles, and they're contained in that ground mass, which is what the finer material is called that it's found in. Those pebbles are found in. And then you've got sandstone. It feels just like sandpaper, if you ever felt sandpaper, that size of a particle. Shale and mudstone or siltstone, very fine particles, clay minerals usually. And that can be a lot of different things. Clay minerals are a wide range of minerals. Shale forms in very quiet water environments, so lakes, Gulf of Mexico, the deep ocean. The clay is deposited and lays down very horizontally. Clay particles are like the micas you saw. They're very thin and want to lie parallel to each other. So that property has them form thin layers, and you can see sometimes these layers in the shale. Shale is easily split apart, just like the micas you saw, and that's called a fissile texture. It has a fissility. Shale crumbles very easily. You don't really want to build something heavy or expensive on like a shale cliff. Rainwater gets in between the layers of clay minerals and will make them expand, and then they crumble, and it weathers pretty easily. But it's the most abundant sedimentary rock. And you can find lots of different fossils in shale. We have some in the lab that I'm going to show you from Kentucky that have plants. Sometimes you'll find other marine creatures in shale. This is a part of the Grand Canyon, and the Grand Canyon is very good for showing all types of geologic features. So the shale near the bottom there of the figure has crumbled and weathered, broken apart more easily. But these rocks, these layers or beds, are more resistant to weathering. So sandstone and limestone don't weather as easily as shale does. Sandstone can form in all kinds of environments. So dunes, beach, lakes, lots of river deltas. Second most abundant sedimentary rock, mostly quartz. The nice yellow sandstone you might see, or yellow sandpaper, that's pretty much all quartz. But of course, sandstone is not going to be perfectly 100% quartz. There are types of sandstone that might have a lot of the orthoclase or pink feldspar, and that's an arkose. Greywacky, it's a German word, and I keep meaning to look it up to try to remember the meaning. But greywacky is quartz sandstone plus lots of other things, usually clay. And I've got a piece in the lab to show you that. There's a whole sedimentary geology subset of identifying and classifying the different rocks based on the percentages of what minerals might be in there. This is the type of quartz sandstone you might see. You can see that there are some layers in there, slightly different color. So this is just impurities that have been laid down with the grains. Then if you look at it close up, you'll see there are lots of rounded grains, all about the same size. So those grains are all about the same size. That means the rock and the sediment is well sorted. The grains all have about the same size, the particles. If the grains are different sizes, if you have large ones and small ones like in a conglomerate, then it's called poorly sorted. This is another visual tool to help identify what the depositional environment, was it a lake, was it a beach, was it a river delta? So if you are familiar with what these things can show you, you can look at an outcrop and say, oh yeah, that was that and that and that, get a basic idea. Particle or grain shape can be very rounded or kind of angular. Angular particles are not transported very far from where they eroded and broke down. Very rounded particles have been transported a lot further. They've been rolling and rubbing against each other in the water, and all those sharp angles and points have been broken off. I like diagrams, and I'm glad I've got these because I can't draw, so I've got these great diagrams to show you. There's also a diagram kind of like this in the back of your lab book. So you can see very poorly sorted or poorly sorted, lots of different sizes of grains, and well sorted, the grains are all about the same size. Then the grains can either be angular, or depending on if they're kind of round or kind of flat to begin with. And then the more and farther they're transported, the more rounded they get to. Conglomerate and breccia. Conglomerate is usually lots of the fine matrix, and it has a fair amount of gravel-sized or larger rounded grains in it. So a lot like this. This picture is probably an old riverbed because it's got these large kind of boulderies and then gets very small. So this is a very poorly sorted rock right here. The breccia has the same fine ground mass with angular larger particles. So these are kind of typical. That other figure previously had the conglomerate as mostly gray. You can have all kinds of stuff. It can be almost anything, whatever's been transported by the river. So these black are probably shale. It's hard for me to see, to exactly tell something from a photo. So the one on the left is conglomerate and the one on the right is a breccia. Does somebody have a question? Oh, there we go. All right. Hello. Come on. All right. Chemical sedimentary rocks form from a material that has been dissolved in water and then gets precipitated out when the water evaporates enough, and the water will be super saturated with whatever that material is, and then it will precipitate out. These are things like limestone, chert, salt. They're all different kinds of salts, so it can be almost any type. Like in the Dead Sea, that water is super salty that people can float in it. As that water evaporates, then the salt crystallizes at the bottom. So it can be, chemical processes can be either inorganic, like evaporation or some kind of chemical precipitation, or they can be biochemical, and that just means that the sediments were created by things like coral, usually marine creatures, coral, mussels, you know, whatever, sponges, all that kind of stuff. When whatever it is, the coral, the sponge dies, then the skeletons will get damaged and broken apart and degraded into smaller particles. Usually with biochemical sedimentary rocks, there are fossils, or there can be a lot of the time. All right, limestone, the most abundant chemical sedimentary rock, especially in Kentucky, composed mostly of calcite. You saw in your lab book last night there was a rock called dolomite. Well, that's also calcite, but it's got magnesium in there along with the calcium. That rock also will fizz in acid because it has calcium carbonate. It's kind of rare, and we don't know how that happens or why the magnesium gets into that crystal lattice and moves calcium out of the way. But either way, limestone can form either organically, like corals and sponges create calcite skeletal material. If that stays in place, then that's a biochemical. If that material gets broken up and then transported somewhere, then that's inorganic as well. It's kind of a grayish area, and it kind of depends on the site you're at. But also limestone can be created by calcite being deposited out of precipitation, chemically deposited. So biochemical limestone comes from the shells and skeletons of marine creatures, usually around a coral reef, like the Australia's Great Barrier Reef. You also might get a rock called coquina, and basically it's just shells that have been compressed and not really well turned into rock, but kind of squished together. Chalk actually is composed of microscopic plankton, marine organisms, skeletal material. Over thousands, millions of years, when the plankton dies, that skeletal material rains down and lands on the seafloor, builds up over time, gets buried, lithifies, turns into chalk. So the chalk cliffs of Dover, yeah, they're really tall, and that's what they're made of. That's kind of wild. So here's what coquina might look like. This will form kind of in the tropics. shells that have just kind of been cemented a little bit together. Yeah, the Great Barrier Reef is one of the largest reefs. Sorry, my dog's scratching on the floor because she thinks she can make a nest on the floor. And then this on the right, this is an ancient reef from Permian 60, oh crap, I forget. Millions and millions of years ago. I have to pick that up in my head again. From Texas. So this barrier reef was covered over by sediments and remained in place. Then over time, sediments being deposited on top and top lithified the whole thing into a large piece of limestone. So this is in Texas. Oh yeah, so here's the chalk cliffs. I believe this is Dover. I forget how tall that is, but it's like hundreds of feet tall. And in that inset photo, those are a plankton type. It's actually I think they're an animal. Those are called coccoliths, and they create those shells there, and those little pieces slough off and fall down, and that's what has created most of that chalk there. So inorganic limestone, probably the easiest type to see is stalactites and stalagmites in caves. Water will transport calcium carbonate in solution. It's dissolved in the water, and when it gets saturated enough, supersaturated, it will crystallize out and precipitate out. So travertine, that's the type of limestone that you see stalactites and stalagmites are made out of. And we'll talk about caves a little more later. Oolitic limestone, that's a fun word. I've got some in the lab to show you. I've got some of both of these. It's actually tiny little, there's a photo coming up, I think it's easier to see. So calcite crystals form stalagmites and stalactites, water dripping in the cave. So here's an oolitic limestone. It looks like sandstone, it feels like sandstone, but it's made up of these tiny little circular bits of calcite that have rolled around in a tropical area in like a calcite goop that has formed just really oversaturated calcite area, and they form like snowballs, and they will lithify into a rock. If you were to slice this rock open and look at it under magnification, you would see all the little circles and the layers of it. They look like gobstoppers, tiny little gobstoppers, but you'll be able to see all the layers in the little ooids. Dolostone made up of dolomite, which I wish we had. I have a little piece to show you, and that's what I forgot. So next time I have a little piece to show you. I'm not quite sure how it forms, but somehow high magnesium rich water moves through limestone and will replace the calcium with magnesium. Chert is microcrystalline quartz. So it's precipitated out of water and does not form those nice pointed long crystals of quartz that you saw. They are just crystallized out and do not have the space to get very large. So flint, agate, jasper, they're all quartz chert because it's chert because it's microcrystalline, very smooth, and you can't see the particles without any magnification. So this is an example of what those might look like. Flint, jasper, chert, and they're very strong, used in Native people's tools. Petrified wood, Lauren, you asked me about that last night. It's quartz that has been transported by water through the tree in this case and crystallized out, precipitated out, and turned into quartz.
Yeah, it's just so cool to me.
It is cool. Another type of chemical sedimentary rock, again formed by evaporation of water. Rock salt and gypsum. The gypsum you saw was a crystal gypsum. It had the space to grow a large crystal. If you have an evaporite salt and gypsum, those are very tiny particles. They don't have space and enough, well, usually space to grow very large. They're just constantly being covered by other material. These are pretty common, and a lot of folks, I think India and parts of really dry Africa and in California, they evaporate water in really hot places and then collect the salt for use. And salt flats like in Utah, is that Nevada? No, not Nevada, Idaho. So the Bonneville salt flats, I think that's where they tested. Is that where they tested the first rocket? Well, anyway, so here's the Great Salt Lake. These salt flats used to be covered with more of the Great Salt Lake, but all that water has since evaporated. There's not much rain to replenish it. So you got all the salt flats right here. Coal is an organic sedimentary rock, and it forms from mostly plant material. Forms in swamps, then trees or other plants, algae, plant spores, all that kind of stuff falls into the water, sinks down to the bottom, gets constantly covered and put under pressure, eventually lithifies into coal. So the carbon is what's left. The pressure and heat goes along with pressure. The deeper something is buried, the warmer it's going to be. So both of these help lithify material. Sometimes you can see leaves, bark, and wood in coal. I've got something cool to show you in lab, and I'll wait to show you that in lab. In Kentucky, our coal seams are very thin, maybe no more than 10 feet, especially in eastern Kentucky. They're all different thicknesses. Some are like a foot thick. Our coal is surrounded above and below by black shale, and then it gets grayer and less carbon as you go away from that coal seam. That's something that we've observed, especially in eastern Kentucky. So coal forms in 4 stages. You get plant remains being deposited in a wet, swampy area, turns into what's called peat, then lignite, bituminous, and maybe anthracite. So we start out with what's called peat, basically plant material that has been compressed a bit, and the water, most of the water and dirt and what else has kind of been squeezed out. This is still used in Ireland as a heat source. With more sediment piling on top over time, so this takes millions of years. More sediment coming on top, more burial and more pressure will push other things out of the coal, push water out, push out other minerals, and it turns into lignite, which is also used, but it doesn't have as much carbon content, and so it has less efficiency. Bituminous, that's what we have in Kentucky. That is the most common thing that we mine, and it has a much higher heat capacity, heat efficiency. And anthracite forms through plate tectonic activity. So on the left there you see what looks like hills. So that piece of land or crust has been compressed, and that really turns the bituminous coal into shiny anthracite. There are some deposits in Pennsylvania and West Virginia. And anthracite has the highest heat efficiency, heat capacity. So lithification is kind of is part of turning sediments into rocks. Lots of different things can and do happen in different areas. So diagenesis, that's the umbrella term for everything. It includes any and all chemical, physical, biological changes. In this case, the example they give, well, formation of coal, and one thing that happens is that minerals will recrystallize into more stable minerals. So lithification is actually the process of compaction of sediments and cementation of the mineral grains, or the mineral grains. If you think about a sponge, your kitchen sponge, think about the actual sponge part as mineral grains, say sandstone. Then you've got all these pore spaces in between. You can hold it under the tap and watch water flow through it. That's exactly what a sandstone is like, with a little bit of cementation between the grains. Here, I like this picture. So the top there is clay particles being transported, and when they are deposited and then compacted, they get pushed into flat layers, and then the pressure forces them to lithify, turn into rock. And the bottom one, that's the cementation. So think of those as sand grains, and you see those little blue arrows there flowing. That's water flowing through those pore spaces. Cementing is the water dissolving a little bit of whatever the mineral grains are and then precipitating it in another part of the rock. So it's just like putting mortar in between bricks. When you're building a brick or concrete wall, cement is like the mortar that holds it all together. Okay. Classifying sedimentary rocks. So this is what you're going to do in lab. So we've got detrital, and detrital has what's called a clastic texture. Texture in geology doesn't mean how it feels, it means particle size. What do the grains or particles look like? Are they large? Are they small? Are they rounded? Are they angular? So detrital is material that's been cemented together, lithified that way. Chemical and organic or biochemical has a crystalline texture. Very small particles that are interlocked, the grains have I can't think of it, have lithified together and I guess interlocked. And sometimes you cannot see the crystals. You cannot see the size, so very small or fine texture. So these are different varieties, and you're going to see most of these in lab actually. So you'll see that if you have a siltstone or shale, you won't be able to see the particles without some serious magnification. And they're made up of mud or clay particles. Quartz, chert, same thing, you won't be able to see it. Most limestone, you won't be able to see it. But if it has fossils in it and it reacts to the hydrochloric acid, then you definitely know you have limestone. So that's one way to tell, process of elimination. If you have a fine-grained, fine-textured rock, try putting some acid on it. If it bubbles, you know you've got limestone. If it doesn't, then you can at least eliminate that, and you can think, well, what else might it be? Probably clay or silica or quartz. So, all right, so here's the fun part. At least to me, I had a great professor as an undergrad, and we talked about this stuff all the time. It was just fascinating. So sedimentary rocks show what the environment was like in the past. Sedimentary environment. So you think of one spot, maybe the spot where you're sitting or standing. What's underneath you? How did the environment change from however many millions of years ago or whatever up to the point where you're at now? So sediments are always accumulating in one spot. And again, you can look at a column or an outcrop or even a drilling core, which I get to show you some of that. And if you know where the bottom and the top are, you can actually look at the rock, and depending on its composition of different minerals, you can figure out what the environments were like. There are three larger categories or broad categories. Continental, on the continents; marine, in the ocean; transitional is more like a beach and a lagoon area, transitional between the continent and marine. On the continent, rivers and streams do most of the rock erosion and degrading and depositing of sediments. When we had a glacial periods, or more than one glacial period, glaciers are incredibly powerful. They will plow along. So think of miles thick of ice, plowing along, destroying the soil, picking up rock and sediment in the bottom there, moving it along. When it melts, it deposits it, you know, much farther than where it picked it up. Wind can also sort sediments. Usually they're very fine that the wind can actually carry and bring somewhere else. Marine, you can have shallow marine. This is where rivers usually deposit the finest material that they've been transporting. And coral reefs will deposit their calcium carbonate right there. Deep marine, these are the very fine sediments. This is where we'll get shale forming. There might be some submarine landslides of some other sand and whatnot material. But mostly the sediments on the ocean floor are going to be some type of a clay or shale material. Transitional, you can have beaches, there we go, tidal flats, barrier islands, lagoons, deltas, something with clay and sand mixed somehow. You get some of both. And I'll let you look at that diagram if you can actually read. I'll let you look at that yourself. This is kind of cool. If you're drilling down into the ground, into the rock, or you're looking at an outcrop, you're standing in one place, and let's say at the bottom it's limestone. Then as you go younger and younger, oh, it's turning into sandstone, it's grading into sandstone, and then it's pure sandstone. These are different sedimentary facies. The facies is what the environment was like, kind of all together. Different. So if it's all limestone, that was probably a reef area, and sea level rises and falls over time. So then if you have sand that's younger, then the sea level has dropped because sand would be the beach. I know this is probably hard to imagine, but not all rocks have a solid boom contact in between showing a reef limestone and a beach sandstone. They're not going to be, or they're not going to be butted up next to each other like that. They're going to be a gradational transition. The sea level doesn't rise and fall very quickly unless it's a major disaster. It takes a very long time for sea level to rise and fall. So sedimentary rocks, there's actually some structure to them. That picture of the Grand Canyon, you saw blocks of rock. Those are called strata, beds, rock layers. I might say layers. All three mean the same thing. Layers of rock that have the same basic composition and characteristics to it. Bedding planes are thinner pieces of whatever layers you're talking about. And cross bedding, this is kind of neat. It's like wavy bedding planes. This occurs in dunes and deltas. Mammoth Cave, if you ever go to Mammoth Cave and you go on the tour where you go down those big steps, I forget which one it is, down the really long steps. I went there one time with my dad, and the ranger was pointing to the bats up in the ceiling, and that was really cool, but they was pretty tall. So I just looking around, and there was some cross bedding in the wall, and I just went over there to look at it. So right there's some cross bedding in the limestone there in the wall. So here's again a cliff of rocks. You might see this along the Kentucky River as well. So the bedding planes would be some type of a break in between some of these layers. Here's cross bedding. So this is actually a living sand dune, and then this is a sandstone, and the cross bedding was preserved. So this is created by water. So this would be water flowing this way to the right, and then it was flowing to the left, and it was flowing to the right. So a beach or a dune where the sand gets moved around a lot. Graded beds, I'm just going to mention this. They are very useful to tell you what kind of, let's say you have a delta or a river mouth and sediments being deposited out, or in this case, a deep sea delta. Graded beds are large particles on the bottom, and then it grades into very, very small on top. Then they'll be large and they grade into small again. So this kind of deposit over time tells you kind of about that kind of stuff. Ripple marks are waves preserved in rock. Mud cracks, same thing. And fossils. Fossils are a sedimentary structure. Ripple marks, they're pretty neat if you ever see anything like that. And then these are mud cracks. So the mud has dried out, and then it kind of lifted up on the edges, filled in with more sediment, and got buried and preserved in that shape and structure right there. Okay, sedimentary rocks are a big, big part of the carbon cycle, the carbon dioxide cycle. The ocean actually can store gases. It can store atmospheric gases. It stores a fair amount of carbon dioxide. Limestone and corals and sponges, anything that makes a shell out of calcite, stores carbon and carbon dioxide in that material. Limestone, it's a sink, it's called, stores it. When limestone gets eroded, and like you're putting the acid on it or acid rain, it releases that carbon dioxide back into the atmosphere. Trees and plants absorb carbon dioxide as well and hold on to it until they die, and then it gets released. So the fossil fuels we use are a big sink of carbon dioxide as well, but they were created millions of years ago, and they take millions of years to create. So when we burn carbon-rich material, then that's released back into the atmosphere, and it doesn't get back into one of those sinks nearly as fast as we put it out in the atmosphere. Volcanoes also release carbon dioxide, but that's not nearly as much as in the fossil fuels that we are burning. So limestone holds on to most, largest repository of carbon, holds on to most of the carbon from carbon dioxide. So these are all the different ways carbon dioxide moves from rocks, the ocean, plants, land into the atmosphere and back. So it's a complicated, always moving cycle. So stop sharing. Okay. All right. Does anybody have any questions?
No, ma'am.
No. No. Okay. No. No. Okay. Does anybody, if you need pages for assignments, hang on so I can get your name, or you can just email me and I will send you those.
I have a question about the next pre-lab.
Uh-huh.
So the pre-lab quiz, will we do that tonight or will we wait until Tuesday?
You can wait till Tuesday. I haven't made it visible to you yet.
Okay.
Because I didn't want you to, you know, to look through it until you've seen this lecture at least. So you can wait. I'll make it public tonight or tomorrow. How about tomorrow? I'll make it public tomorrow, and so you're welcome to do it then if you like.
All right. Thank you.
Okay. And a couple of you that came in late, quizzes on Canvas don't really like short answers. I have to go in and look at all your answers, and I will correct anything. I will physically change your grade with any corrections. So. Well, okay. All right. Well, if nobody has any questions, you're free to go. If you ever do have questions, please feel free to email me.
Alrighty. Have a good night.
You too. Yeah, if you need some pages from the book, hang on.
Thank you.
You're welcome. So yeah, Bethany, I know you do, and Hunter, you need some pages from the book that you missing. And Hannah.
Well, I got the book, but I don't know what pages like should be there or shouldn't be there, so I don't know if I'm like missing something or not.
Gotcha. Okay.
Like
so
the book was untouched, but it was used. So
okay. Well, for the minerals activities, it's pages 97 through 99.
okay. I have those, so.
Okay, well that should be good.
Okay.
Well, if you see in the future assignments you're missing pages, let me know.
Okay.
Okay. Don't just tough it out. Let me know, and I'll send you some of those.
All right, thank you.
You're welcome. So Hunter, do you need anything? Are you there? Nope. Okay, well, if you do need something, let me know.